Hello everyone, welcome back to Physics 425. In the last couple of videos, we've been discussing mechanisms of heat transfer. And we've talked about heat transfer via radiation and heat transfer by conduction through a gas. So today what I want to start talking about is heat transfer by conduction again, but this time through a solid. One of the goals of this video will be to derive the 1D heat equation. And we'll do this in a few steps, and hopefully along the way we'll come up with some useful insights. So step one is just to try to come up with an expression for the heat stored in a rod, or equivalently the internal energy of the rod. Okay, so we'll start by writing down the heat capacity. And so the heat capacity is going to be determined by the specific heat per unit mass multiplied by the mass of the rod. And I'm going to write the mass as the density, mass per unit volume, times volume. And so this is the specific heat per unit mass. So we know that the specific heat tells us by how much do we have to change the energy, how much heat do we have to add in order to cause a certain temperature change. Okay. So that means if we multiply by dt and then integrate, we could say that the change in internal energy is rho v cv times delta t, where we've assumed that the specific heat is temperature independent for a small temperature change. Okay, in that case, the change in internal energy can be related to the temperature change, or identifying the subscripts 2, U2 and T2, and the subscripts 1, U1 and T1, we could write that the internal energy of the rod is rho v cv times T. And so this is going to be our expression for the heat in the rod at temperature T. I just want to make a little side note here that this is actually pretty similar to what we had for an ideal gas, because in an ideal gas, the internal energy was F over 2 NKB times T, where F was the number of degrees of freedom. And so if we take these prefactors and call them some constant C, then for a gas of fixed particle number, then U would be a constant times T. And over here, actually, maybe it's better to do that over here. If we take the rho v cv, the mass times specific heat per unit mass, then that's just the heat capacity, C, which we're treating as a constant, and we have U is equal to C times T. And so the two expressions are pretty similar. Okay. That's step one. Step two is going to be to write down Fourier's law of heat transfer. And so there, the heat flux is the heat per unit time per unit area, and that's minus kappa times the temperature gradient. We also actually used the same expression when we were talking about the thermal conductivity of a gas. And really what this Fourier's law does for us is it defines the thermal conductivity of a material. And so let's just remind ourselves of what these various quantities represent. And so little q dot is the heat flux. Big Q dot is the power, and then when we divide by A, we have the power per unit area. Kappa is our thermal conductivity. You'll notice that I've written the temperature gradient dt dx as a partial derivative. That's because at some point what we're going to do is we're going to realize that the temperature can also change with time, and so temperature will depend both on the position x along the rod and on the time. Okay, so let's think about a specific scenario. So here's our rod. We'll set the left-hand side of the rod to be temperature T1, and we'll call that the high temperature side. And the right-hand side will be temperature T2, and this will be the low temperature side. We'll make the rod length L, and we expect a heat flux to flow from the high temperature side to the low temperature side, and we'll indicate an x coordinate that increases from left to right. Okay, so in the case drawn, the temperature gradient is negative because as we move along positive x from left to right, the temperature decreases. And so therefore q dot, if we go back to Fourier's law, if we have a negative temperature gradient and there's a negative sign in Fourier's law, those two negatives cancel out and q dot becomes positive. And so we get a heat flux from left to right, which was expected. So q dot is positive, so heat flows from left to right along positive x. Okay. So in general, kappa can be temperature dependent. And so if we write down Fourier's law, I'm going to call q dot the power now. So we have power per unit area is minus kappa, and we'll put in the explicit temperature dependence, and this is dt dx. Okay, so if for the moment we're only interested in the situation at one particular instant in time, we can forget about the time dependence of the temperature, and we could write that p dx is going to be equal to minus a kappa of t dt. And then we can integrate, and so we're going to integrate on the left-hand side, we'll integrate with respect to x from one end of the rod to the other. So if the rod is length L, we'll get P times L. Then we have minus A. And at the left-hand side, we have temperature T1, and at the right-hand side, we have temperature T2, and then we get kappa dt. Okay, so in this next step, I'm going to do something a little strange. I'm going to multiply by the absolute value of the temperature difference. And then if I want the equality to hold, I have to divide by the same amount. Let's just note that, remember, T2 is the low temperature side, so T2 minus T1 is actually negative, but we have it in an absolute value sign in this case, so it's a positive quantity. overall. And then we still have our integral here. So what I want to do is just isolate the stuff above this brace that I've drawn. And so it's the integral of kappa between two limits divided by the difference in those limits. And if you remember from calculus, this is just the definition of an average value. And so this is the average value of kappa between the limits t1 and t2. So what does this expression actually calculate? The integral of kappa divided by the temperature range, the difference in temperatures. If we were to plot kappa as a function of temperature, and let's suppose it looked something like this, and then we go and identify T1 and T2. Well, what that integral represents is just the area under the function. And then if we divide by, so the integral is the area. And then if we divide by the temperature range, then that's just equal to the average height of the function. And so if we draw in the average height of the function, it might be something like this. And so now the red shaded area is equal to the black shaded area. So we have a little bit of extra area here, but that cancels with the missing area. Maybe I'll draw it in a different color. This is the missing area. Okay, and so this red dashed line represents the average value of kappa between the two limits of integration. Okay, so if we take this equation star and rewrite it, what we've got is that, remember on the left-hand side we had P times L, and that's going to be equal to minus A times this temperature difference, and then it's times now this integral represents the average value of kappa. Okay, good. So in our scenario, T1 is the hot side, so it's greater than T2, and so that means T2 minus T1, as we said, would be negative, so therefore minus T2 minus T1 is equal to T2 minus T1, right? Because we have this difference in an absolute value sign, and then we multiply by a negative, so overall it's the difference in temperatures and a negative sign. And so this results in the same negative difference in temperatures. Okay, and so we're just going to call that delta T. So our power times L is going to be A, and then minus the absolute value of T2 minus T1 is equivalent to delta T. And then we've got the average of the thermal conductivity, or delta T is equal to 1 over kappa bar times L over A times P. And so this might remind you of something. This is reminiscent of a voltage difference is equal to resistance times I, but resistance is resistivity L over A, and then we have I, or resistivity is 1 over conductivity L over A times I. And so we have an inverse of a conductivity and inverse of conductivity, and we have an L over A factor, L over A, and then we have instead of current I, we have a power P, and instead of a voltage difference, delta V, we have a temperature difference, delta T, but the structure is the same. And so this is like our electrical circuit, delta V, in our thermal circuit. So let's say thermal circuit equivalence. Voltage difference goes to a temperature difference. Electrical conductivity goes to thermal conductivity. One of the differences here is that we said our thermal conductivity could be temperature dependent, whereas usually if we're talking about some kind of conductor and electrical current flow, the conductivity doesn't depend on the voltage applied across the material. So that's one difference, but it's still an electrical conductivity related to a thermal conductivity. L over A is the same, and then our current goes to power, or actually, let's do it this way. Our current, which is charge per unit time, goes to a power, which is equal to a heat flow per unit time. So instead of conducting electricity, charge, we're conducting heat. Okay, so the claim then is we can often treat heat transfer by conduction using an equivalent circuit analogy. Right, so if we just thought of an equivalent circuit, let's just draw a simple circuit with a battery and a resistor. So instead of a voltage difference, we have some temperature difference, which is driving not current flow, but heat flow. And we have a thermal resistance. And so if we did a Kirchhoff loop rule, we would say delta T minus the temperature difference dropped across our thermal resistance, which is PR, is going to be equal to 0, or delta T is P R times T, or R times T, where R times T is the average thermal conductivity inverse times L over A, and that's our thermal resistance. Okay, good. I think we're going to come back to thermal circuits in a little bit, but before doing that, let's consider step 3, and this is where we're going to try to come up with a derivation of the heat equation. So consider a section of rod with heat flux Q dot, and we're going to consider conservation of energy. Okay, so we'll start with the similar type of drawing that we had before. So here's a rod of length L. We'll keep the left-hand side as high temperature, and the right hand side as low temperature. We'll say over here this is x equals 0 and this is x equals L. And we have heat flux Q dot in the rod, and we're going to consider a section of this rod. And so we'll call this coordinate x, and at the end of the section the coordinate is x plus delta x. Just so that we have something in mind, I want to suppose that we had some kind of temperature profile for the rod. We know that on the left we have the high temperature side, and then it gets the temperature reduces as we go to the right. And so let's just suppose that we had some kind of temperature profile that looks like this. And then over here we have our position x, and then over here we have position x plus delta x. So what we're going to end up considering are the temperature gradients at these different positions. And so at position x, we're going to have dt dx evaluated at x. And at position x plus dx, delta x, we'll have dt dx evaluated at x plus delta x. So these temperature gradients are going to come from the Fourier's law. Okay, good. So let's have that picture in mind. And the first thing we'll do is we'll write down the heat within the shaded segment. And so like we did before, we'll say the heat is the, it's going to be the mass times the specific heat per unit mass times the temperature. And so now we'll allow for the fact that the temperature is going to be also time dependent. Okay, but the volume of this segment is, if we consider the rod having cross-sectional area A, the volume is A times delta X. And so the heat then we could write as rho CV, and for volume we write A delta X, which looks like I'm going to write dx here. Actually, I'm going to change that to delta X. So A delta X is the volume, and then we have temperature. Okay, so that was step one that we did before, where we wrote down just the heat or the internal energy of the rod. Okay, so now we do our conservation of energy. Because we have a heat flux, we're going to have some energy flowing into the segment and some energy flowing out. So the change of energy in our segment in a time delta t. Okay, so this is going to be equal to the heat in from the left minus the heat out to the right. Okay, so the change in energy, we know that the internal energy of the rod is rho V, but V is A delta X CV times the temperature. And so we're going to assume that we're going to have temperature T at time T plus delta T. So that's the final energy, and then we subtract the initial energy. And so a lot of this stuff is the same. All the prefactors are the same. It's just that we have the temperature at a different time, at the initial time t. Okay, and then from Fourier's law, the heat flux was minus kappa, minus kappa dt dx. And so we're going to have the heat in from the left, and so that's at position x, and so the left side is at position x here. And so we don't want the heat flux, we want the actual heat. And so heat flux is the heat per unit time per unit area. So if we multiply by delta T and A, that's the heat from the left, and this is due to Fourier's law. So this is heat in from the left. And we do something similar for the heat from the right, but we're going to subtract that, and we're going to have a minus kappa dt dx, but this is going to be at the right hand side, the right hand edge of our segment, x plus delta x. And so that's why we're allowing for the fact that the slope in Fourier's law can change with position. Okay, so this is the heat flux. So again, we have delta T times A. And so this is the heat from the right. And so we're subtracting that off because that heat is leaving our segment. Okay, good. So this factor of area is in all four of our terms, and so we can cancel that out. And so what do we have left over? We have rho CV, and then we have, let's see, T of x times T plus delta T, and then we have minus T of xt, and then we still have a delta x factor. And so that's the left-hand side of our equation. And on the right-hand side, we've got a kappa. And let's see, we have a minus and a minus, so that's the positive term. And so we have dt dx at x plus delta x. And then we have a minus, so just one minus here, dt dx at x. And then they're both multiplying delta t. Okay, so we can rearrange things a little bit. In particular, the important step is to divide by delta x and delta t. And so we can get t, x of t plus delta t minus t of x and t. And then we divide by delta t is equal, we'll put all the constants over here. This is kappa rho CV. And then we have dt dx at x plus delta x minus dt dx at x divided by delta x, like so. And so now you could probably see what's going to happen is we're going to take the limit that delta t and delta x go to 0, and on the right hand side what we have is a time derivative of the temperature is equal to some constants, kappa over rho CV, times its two position derivatives of temperature. And so that's d2t dx2, or this is commonly written as dt, so temperature is a function of x in position, is equal to alpha d2t xt and dx2. And so this is the 1D heat equation. So it's a second order differential equation, and alpha, a partial differential equation, alpha is defined as this ratio of constants, thermal conductivity. I shouldn't say constants because kappa and CV can both be temperature dependent. So let's say a ratio of thermodynamic quantities. And this is the thermal diffusivity is what alpha is called. The units of alpha, if you do a unit analysis, thermal conductivity is watts per meter Kelvin. Rho is kilograms per meters cubed, but we have the inverse of rho. And so we have kilograms meters cubed. And then specific heat is joules per Kelvin, but we have a specific heat per unit mass, so it's joules per Kelvin kilogram. And then again, we have the inverse of that. So we have joules on the bottom, kilograms Kelvin. And so kelvins cancel, kilograms cancel, meter takes meter cubed to meter squared. Watts is a joule per second, but we have 1 over joules, and so this ends up being meter squared per second. Okay. So that was one of our goals, is to get that 1D heat equation. We may come back and look at this again, but let's do a little bit more on thermal circuits because it's pretty neat, I think. What we saw so far of our thermal circuit was it was just like a resistor and a battery, right? Just heat flow along a rod between with 2 different temperatures at its end. It was just like a battery and resistor circuit. So let's do something a little more complicated. Let's take a rod, and it has thermal conductivity kappa, and then we're going to stick it onto the end of some large thermal mass, like a block of copper or something. And so this thermal mass is at temperature T, and so these are going to be different materials. The rod is going to be, say, material 1. It might be a piece of brass or something like that, and the block is material 2, and it's like a chunk of copper. And what we're going to do is we're going to say that material 2 has some specific heat. Okay, we'll make our rod length L, like so. And it's going to have some cross-sectional area A. And we're going to imagine that there's some heat flow, Q dot or P. So some assumptions that we're going to make. So we're going to assume that the heat capacity of material 1 is very small compared to that of material 2. And so we can do that just by making the volume of material 1 much less than the volume of material 2. And so what this assumption implies is that there's no power absorbed by 1. So material 1 is just a conduit for heat flow. It's 1 just provides heat transfer. Okay, so it has a temperature gradient across it, but it doesn't store any substantial heat. And so we'll say that at one end of the rod is temperature T0, and then the other end is at temperature T, connected to this large mass. Okay, so the other assumption is we assume that the thermal conductivity of 2 is very high. And so that means that there's just no temperature gradient across material 2. It's just always at a uniform isothermal temperature. And so that's why I was talking about it as if it was copper, because copper has a very high thermal conductivity. Okay, so our assumption implies that temperature of material 2 is always uniform. So it's an isothermal block of material. Okay, so by Fourier's law, Q dot in 1 is just related to its temperature difference and the thermal conductivity. So the flux is Q dot over A is the average thermal conductivity divided by L times delta T. Okay, because the heat, remember we had the temperature gradient dt dx, and so we're just assuming that this dt dx is a temperature difference, and then delta x is the length of the rod. Okay, and so one result is that the power, Q dot, is A over L times the average thermal conductivity times the temperature difference, which is T naught minus T. Okay, then step 2 is material 2 absorbs incident heat and we can relate that to the heat capacity of material 2. So delta U is divided by delta T is going to be rho V CV. So then we divide by the change in temperature, multiply by the change in temperature and divide by the time interval. So Q dot is delta U divided by the time interval is rho V CV times dt, the temperature gradient. All right, so we have two expressions for Q dot now. So let's equate the Q dot expressions. From the first step, we had Q dot is A over L, average of the thermal conductivity and a temperature difference. And then from step 2, we had that was rho V CV dt dt. Or rearranging minus A over L kappa bar, and I'm going to divide by the constants rho V CV is equal to, I pulled out a minus sign, so that means our temperature difference is going to be T minus T0 because I kept a minus sign over here. I divided by these constants, and so then we have dt dt. So then finally, what we could do is say we have minus a over L kappa bar over rho v cv, let's multiply by dt is equal to, dt is in the time interval, is equal to the temperature in dt over t minus t naught. Okay. These constants you could confirm, but if you did a unit analysis of those constants, they would have units of inverse seconds. And so I'm going to define this combination of constants to be a time constant. So it's 1 over tau. Okay, in that case, then we have, on integrating, we'd have minus t over tau would be the integral of dt over t naught, which is equal to the ln of t minus t naught, plus b prime, where this is a integration constant. Actually, because it's a constant, I think I'm just going to make it a minus b prime. Okay, so that means that ln of t minus t naught is equal to b prime minus t over tau, or taking the exponential, exponentiating, t minus t naught is going to be equal to e to the b prime, e to the minus t over tau, and this is just another constant. Let's define it to be just b. Okay, and let's remind ourselves that tau was equal to 1 over these constants, so it's rho v cv L over a times the average thermal conductivity. So T is equal to T naught plus B e to the minus T over tau. So if initially at T is equal to 0, the temperature of our copper block, so let's go way back over here. Here's our copper block, and so we're imagining at some initial time, T equals 0, this temperature of our copper block is at Ti, T initial. Then T initial would be equal to T naught plus B times e to the 0, which is 1, and so therefore B must be equal to T initial minus T naught. And so if we make that substitution, then T as a function of time is going to be T naught plus B, which is T initial minus T naught, e to the minus T over tau. And so if we made a plot of that function, at T equals 0, we would have T naught plus T initial minus T naught. So we're going to be at T initial. And so let's suppose that this is T initial here. Then a long time later, let's say T goes to infinity, then the exponential term vanishes and we end up at T naught. And so in this picture, what we're assuming is that initially this copper block is at some temperature above T0, and then we let the system go, and the copper block will actually cool to T0, and how fast it cools is dependent on our thermal time constant. And so what we've drawn here, actually this Q dot would be negative. So we would have heat flowing out of the large copper block to this temperature T0 at the other end of our rod. And so maybe this other end of the rod is in like a thermal reservoir, like a bath of, I don't know, liquid helium or something like that. And so heat is flowing out of the hot copper block and into our thermal reservoir via our copper rod. And so this is an exponential, and so the time evolution of the temperature looks something like this, and the thermal time constant, if we set T equals to tau, then we get to about over here, and so this is our thermal time constant, and this would be at a temperature of T0 plus Ti minus T0 divided by E. Okay, and so you might have recognized that this is very analogous to just an equivalent circuit that involves a capacitor. It's like the charging or discharging of a capacitor. So this is exactly equivalent to a capacitor with an initial voltage Vi discharging to a final voltage V0 through a resistor R. So how could you actually make that circuit? So suppose we had a capacitor C here, and what we're going to do is we're going to make a switch. And so the switch could be closed either left or right. And so on the right hand side, we have a resistor R and a voltage V0, a battery. So if the switch was closed to the right and we waited a long time, the capacitor would charge to a voltage V0. And on the left hand side, we have a battery with voltage Vi, so that if the switch is closed to the left, the capacitor instantly charges to a voltage Vi. So to mimic our thermal situation, we would first put the switch to left to quickly charge capacitor to V initial. Then we would put switch to the right to discharge the capacitor to V0 through resistor R. So here we're assuming, for this picture, we're assuming that V0 is less than V initial. Okay, and then if you did that, what you would get is, if we plotted the capacitor voltage as a function of time, let's say we had, let's say at t equals 0, before t equals 0, so if times less than t equals 0, then we had our switch to the left. So let's say this is valid for times less than 0, the switch is to the left. Then we're at some voltage V initial. And then over here, it's going to be V0. And let's suppose that we flip the switch to the right at t equals 0. Then the capacitor would discharge to V0. And then there would be a time constant. Tau is equal to RC here. Okay, let's do one last thing. So the thermal time constant. Let's look up what it was. Our thermal time constant was, there it is, rho v CV times L. So it is rho volume CV times L. And then there was A and the average thermal conductivity. Okay. So let me write it this way. 1 over kappa L over A, and then what's left over, rho v CV. So 1 over the thermal conductivity times L over A, that was our thermal resistance. So thermal resistance. And rho v CV is mass times the heat capacity, a specific heat per unit mass, and so that's just the total heat capacity. And so that's going to be our thermal capacitance, which is just the heat capacity of our large block. Thermal capacitance is the heat capacity of the large block. Material 2. And so what we can do is we can set the time to cool or heat material 2, the large block, by adjusting the thermal resistance of the rod, material 1, and or adjusting the capacitance of the block or material 2. And so it's quite a nice thing that a lot of the analysis that we're familiar with from basic circuits can be transferred over to a thermal circuit in, for example, a low temperature system that we're trying to design. Okay, great. Thanks very much. And